Good morning. This presentation will be about nuclear transmutations and mass defect and a simplified explanation with the help of the structured atom model. Yesterday we've already had a poster session. There are two supportive posters for this presentation, so everybody can take a nice look at those again. And I would like to try to start with a findings/introduction, which I have scripted a little bit. The structured atom model is based on the idea that the nucleus has a stable and rigid structure that is responsible for all the attributes of the elements. A key point for this model is that we consider the neutron not to be a fundamental particle since it decays into an electron and a proton. Therefore, our concept is based on the proton-electron model rather than a proton-neutron model. Its physical properties and stability can be derived from its electrodynamic nature. There's no need for a strong force. Norman Cook, for example, has been working on a similar model in the sense that he also recognized a fixed structure for the nucleus, the face-centered cubic model. We have an overlap of ideas and some essential differences. The neutron not being fundamental and the organization of the structure is different as a result of the neutron. The structured atom model is comparable, for example, to the alpha particle model in the sense that it also recognizes recurring geometrical structures inside the nucleus. The only difference there is that we still recognize a few more geometrical structures, which I'll be showing later on, which in specific order and number create all the elements in their isotopes. So last year we attended the ICCF conference for the first time. Thank you. For the first time, so let me start that again. Last year we attended the ICCF conference for the first time, where we showed a partial complete periodic table of the elements. This year we are happy to show a completed periodic table with the structure depicted for every element. What we learned at the 2018 conference in Fort Collins last year was that we're definitely not the only one doing this. Many attempts were made to find the logic and order to calculate the binding energy for all the elements. So we set out to take a good look at this topic of binding energy and how it relates to the structure according to the SAM model. And it should be, because it should work like all the other attributes. So the completed table allowed us to put all the elements in a spreadsheet and apply some simple rudimentary logic to this to see if we could find out how this works. We took each nucleon connection that is in the structure and multiplied that by the binding energy from deuterium, which is 2.225 MeV. The second method was to compare the known geometrical structures with their element and their binding energy, meaning each geometrical building block, or nuclet as we call them, has a fixed known binding energy value. The tetrahedron represents the helium nucleus, for example, and has a known binding energy of 28.297 MeV. Every time we see this nuclet, we know the binding energy therefore as well. So the total is simply adding up all the different nuclets with their binding energy, and we should have a complete binding energy for every element. The graph that we plotted from that showed a few surprises. Let me go to the next slide. So the nucleon method seems to hold true to a certain extent, but it is not very feasible since the structure morphs, as does the number of connection points between the nucleus. We resorted to the known first geometrical groupings, which repeat in the periodic table with known binding energy, and we were able to plot the calculated energy for all the elements from carbon-12 onwards. The correlation holds true, and we were happy with the results as it proved the structure as proposed by Sam. Because of our confidence in Sam and the strong correlation we saw, instead of assuming the approach, but beyond element 30, gallium, something happened. Both data lines started to deviate from each other. The SAM values became constantly higher. This trend continued until the end and is related to the change in the structure of the nucleus, which happens at this point in the periodic table according to SAM. Because of our confidence in SAM and the strong correlation we saw, instead of assuming the approach to be wrong, we looked at another reason. What we found offers a greater understanding of the fission and fusion processes. We can even offer a logical explanation how and why fission products are unequal in mass. A 70-year-old mystery can be solved with the knowledge of the structure of the nucleus. Fission appears to be breaking off parts of the structure, the branches as we call them, and we can calculate energy being released through this process. The branching structure of the nucleus results in internal stress energy, and this in turn is the explanation for the difference in the calculated SAM binding energy curvature, which does not account for the branches and the actual binding energy values. Looking at the experimental results that are available in the public domain leads us to conclude that heavy stable elements can be made to fission under relatively mild circumstances. So this presentation, for the rest, is meant to show you these findings. Here's the table of contents. I'm going to go quickly through the fission of uranium, a summary of the structured atom model. I will be going through that quite quickly. I cannot explain it. I do not have the time for that. We're going to show some nuclear reactions. We're going to go to the binding energy and an interpretation, some supporting evidence, and leaving with the conclusion. So to start off with, here's the average binding energy curvature that I'm sure most are familiar with. It's just to summarize what is our current understanding of binding energy and mass defect. We can see, of course, that the tip point is where iron and nickel are, which is the maximum average binding energy, and then it starts to slope off. The fission enigma. So the enigma is that when we have a fission of heavy elements, we get a very distinct double peak, not like a normal curvature, a normal graph with one peak, normal statistical deviation. We see two distinct points, and up to now, I don't think anybody has been able to offer a satisfying explanation for that. So the structured atom model basics. Before I continue, because I have a lack of time, I have way too much material to explain in such a short time, we will put all this material on our website where everybody can download it and read it back at your leisure. Okay, the summary of the structured atom model. We perceive a duality we call a proton-electron pair with the electromagnetic force acting between them. This force is the causal mechanism for the principle of the densest packing that creates geometrical shapes based on the platonic solids. These geometrical shapes in a specific order and number create all the elements. SAM shows the observed nature and the properties of the elements, and I would like to emphasize that the nucleus is not a lumped together collection of nucleons. The basis for this, the first building block, the first nucleus is the deuteron, and we recognize that, and there's no need, as I mentioned, for a strong force. So we use which we called the new neutron in the beginning, but now we refer to this deuterium concept. This would be the idea of it. We get a 2.225 MeV binding energy. We plotted some information there. This is the concept that we have for the structure. The first two elements where we compare the standard model and the structured atom model. So let's see, oh, excuse me. So here we have the deuteron, and here we have the deuteron, the structured atom model. This is a proton-neutron, this is a proton-proton, and an electron. Hydrogen-free, helium-free, helium-4. It's reminiscent of each other, yet there are some distinct differences. If we continue, we see that the periodic table has a cycle of 8. Every period is like 8 wide. And this is where we pointed that out. So we start with lithium, which is a +1 value. We go to a beryllium, which is a +2, boron +3, carbon +4 or -4. There's a switch there. Then we go to the nitrogen -3, oxygen -2, fluorine -1, neon 0. So this is the cycle of 8, if you will. That is the basis of why the periodic table is created, or is as it is. So if we look a little bit further down, we see here the lithium and the sodium. And the lithium is the red lithium nuclide +1. The sodium still has that one lithium nuclide. The rest in white and green is always neutralized, meaning it does not participate in that sense anymore. We can see the periodicity coming back, but there are also distinct differences which explain why, for example, in the oxygen group, oxygen itself is the outlier. It doesn't match with the other elements in the oxygen group. There are explanations there too. In the groups, we can see again lithium, 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 or in the carbon group, carbon, 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 they all come back. Hence, the properties of those elements are also alike. Silicon and carbon are alike. And the noble gases, of course, which is all white and green, that's all neutralized. Everything is neutral. It's complete. It's noble. Doesn't need anything else anymore. It's on its own. So this year, as I said, we finally were able to complete the periodic table, and then it was quite nice. I was not aware of it. We found out, hey, it's the 150th anniversary of the periodic table, so that's a nice coincidence there. The shape of the larger elements. This is important at least to give you the concept of what we're looking at. What we can see here is the structure. It's like an organic, what is it? Organic growth. It's very branched. It's not a lumped together thing. We have in the center here, where I'm pointing right now, that's the first carbon nucleate. So each of those white groups is still a carbon nucleate. And in the center is the first one, and then you can add 2 more, and on that top of that one you can add 2 more, so you get a 1, 2, 4, 8 fractal, if you will, which I point out to the right. And here this is all exactly the same, so this is simply in a fractal picture. This is already showing the nucleates, if you will, and here we just plotted the numbers of those nucleates. So note that the first carbon is 12, and all the other carbon nucleates are 11. That is due to an overlap of 1 proton, of 1 nucleon, which is part of both structures. Hence, it's -1, 11. Another important point is that there is a point of interference where the branches want to occupy the same point. I'm going to point here, the carbon nucleate is blue. And on this side, that's where the next carbon nucleate should be growing. However, they are so close to each other that they will interfere, hence instability. That means at lead is the last, lead/bismuth, is the last stable element. If you follow this logic, that means every other element after that is, per definition, unstable. That means also we conclude there is no island of stability. Observational data when we developed this program was neutron-proton ratio, valence or oxidation state, isotopes and stability, nuclear reactions, nuclear spin. These attributes, these observations were used to create the whole model. So SAM, the next-gen model, it's a bit presumptuous, but there you go. In the past, we started out with a couple of models like a gas, liquid, shell model, alpha particle model, of course Norman Cook with the FCC model, and we believe that we are very close to each other, even though there are some distinct differences. The competition, so to put all these models that in the past century together, we plotted SAM there, basically going way back all to the central potential well model, meaning there's a central attraction force that creates the sphere of the whole nucleus, if you will. So that's where we put ourselves. Oh, excuse me. So the similarities and differences between the structured atom model and the FCC model. I would like to point out 2 major things. The FCC model uses protons and neutrons. This is, of course, the conventional thinking at the moment, whereas SAM uses the protons and nuclear electrons. However, the overlapping is that both stipulate the stability of the nucleus is provided by electromagnetic forces. Therefore, for stability, no strong force or strong interaction is needed. The stability of the nucleus, I would like to point out that when Norman Cook wrote a book with people like Dalla Casa and Paulo Di Sia, and they conclude in their writing by taking the phase relationship into account when calculating the magnetic field effect of 2 circulating charges, an attractive force that exceeds the electrostatic repulsion of the charges is generated. A major component of the so-called nuclear force is therefore likely to be magnetic. And I believe that, where is he? Our friend over there yesterday has made a very good case for that as well. So, the differences between the SAM and the FCC model for specific elements. Here we point out the structured atom model on top. This is the alpha particle, if you will, the alpha particle, the helium-4. And we've shown an oxygen in comparison to what Norman showed. Calcium, zirconium, ytterbium, I believe it is, and lead. So note that the FCC model has a nested geometry, if you will, right? It's always one center and everything grows around that center, like an onion almost. There could be an island of stability in that model. We have, as I just explained, the lead/bismuth is the last stable element, therefore there is no island of stability. So we can see here the major differences between the model. We have an added on or a structure of nucleates combining together, and this is the nested geometry. So that's the major difference, I think. Pointing out nuclear reactions in SAM, I'm going to go in the next slides through these 5 topics here, from beta minus beta plus decay. I'm going to show a sequence of the alpha particle release from uranium all the way down to lead quickly, splitting of the atom cluster fission, if you will, and fusion of nucleates, which is cluster fusion, i.e. cold fusion, LENR, etc. And as a last one, the thorium cycle quickly. So beta minus and beta plus decay. We have over here a neon 23, which is unstable. Take note that the light yellowish spheres are in the normal concept the neutrons, what we call the neutrons. Of course, we have to understand it's a proton-electron conglomerate. When we have 2 neutrons together there, they will form, 2 neutrons will perform beta minus decay. And then you get another pair there, and which creates the next red, we call the lithium nucleate, and therefore it becomes +1. So this is the decay step of beta minus. Reversed, beta plus decay. We take away 1 from the sodium 23, we take away 1. We are left with sodium 22. Then it's not stable anymore because it's unbalanced, and it decays into a neon 22, back to its balanced state. So this is, I believe, depicting beta minus and beta plus decay, the creation or the disintegration of the deuteron building block. Alpha particle decay. From plutonium-239, probably well known, we see on the left an orange structure there, and when that sheds 4 nucleons, which is the alpha particle, you're left with this situation here. So I highlighted where the change is to uranium-235. Another one, thorium-231, protactium-231, which is a beta minus decay step. Then we get the next phase, actinium-227, thorium-227, radium-223, radon-219, radon-219, radon-219 to polonium-215, lead-211, and then 2 beta minus decay steps again, and then a final alpha particle release shedding to lead-207, which completes the cycle and is now stable again. As you can see, here's that confliction, the conflict point, if you will. The red one needs to grow, as I showed in the period, in a cycle of 8, it goes from lithium, beryllium, boron, carbon. So that's where the growth should take place. Take note there are 2 neutrons, if you will, still available. They will migrate to the center, take their place on the red part there, and then it can release again, so that's what you see here, and it can then release another alpha particle. So when we split the atom, we can see here, as we depict uranium-235, and here's some potential fission products that come off. So you get a neodymium, cesium, or a zirconium, barium, and here's the double peak again. So the zirconium would fall in the first peak, and the other 3 would fall in the second peak, which is around 140 AMU. Here we have uranium-235. We have a branch on the right, a branch on the left. I took them off of the nucleus. Take note that there's now a wireframe showing, meaning this is not a stable configuration, which is your fission product, which has to perform several internal transitions, yielding the energy, falling back to its ground state. But the point is that this structure, which is already in the uranium, which is basically the shape of the other normal elements that we know. So these red ones here, they decay, migrate to the center to make a more balanced situation, which leaves you with something like a cesium or a neodymium. The branches that come off, we believe that they first actually come together to collectively break off, forming the first peak. Now the numbers 53 and 38, if you add them up, you're in that 90-ish, 100 region. The remainder is always in that 140 region range. Cluster cluster fusion. So this would be the reversed, actually, of the fission process, which is what we deal with LENR. We can see here an oxygen and a carbon, which is often speculated on, that they come together in a silicon-28. So we show that it's pretty logical to get them together in that way. And yielding energy, of course, exothermic. Here's another one, Palladium 105, which is very interesting because it's a noble metal. Noble metals do not oxidize on the air. And it does not because, believe it or not, the palladium is like on this side, exactly like an oxygen. On the right side, it's exactly like an oxygen. So palladium is like a neutralized big core with 2 oxygens added to it. So it would not be able to break up an O2 in the air because they're very, very similar. When we add a deuteron to the palladium 105, we can get a silver 107. So that should be an easy step. But understand that if we have several stabilizing neutrons not there, like in the isotope 104, it will not work and it will go to a silver 106, decaying back to a palladium 106. Thorium cycle, which India is doing a lot of work on. We can depict that one pretty easily. We have thorium 232, the breeding process. It's plus a neutron, you get a thorium 233, beta decay to protactium 233, another beta decay to uranium 233, which you can use in fission. In reality, it's a bit more complex. They grow a little bit further. But the principle is then you perform the fission in your reactor, and you're left also with a couple of neutrons again, which you use again to enrich the uranium 232. Binding energy. When we try to perform the binding energy, as said, the first method was to simply point out all the connections, if you will. So you can call it a line of connection, and you can simply count them, and there's a logic there. It did not work really well, but approximately, yes, it works. And give me a sec. The deuteron has this binding energy of 2.225, and it's one line of connection, so simply multiply that. Here we see that, the first method, simply calculating the total absolute binding energy. And the second method is the nucleates and their combination, meaning every nucleate, as I mentioned, has a known value of binding energy. That means in the bigger atoms, we can simply look at, okay, which one is there. So I have an example here of, in this case, iridium 191. So we see the prime carbon, which is the center. There's one there. That's always there in the bigger elements. And the number of carbon nucleates, in this case, it has 1 lithium, 9 neutral endings, a couple of extra neutrons. You simply add it up, and you get the number of lines, which you multiply, and then you get your binding energy. Plotted that in a graph, which was quite surprising. We have a very strong correlation all the way up to about element 30, meaning iron, zinc in that region. And then the line started to deviate, which was a big surprise because, you know, that has to be either wrong, there has to be an error somewhere, or there's another explanation. So to show a little bit more detail, this is the delta between 2 elements. So from a hydrogen to a helium, there's a delta in binding energy, and then from the helium to the lithium, a delta binding energy, which we plotted here. In the beginning, you can see it's all really quite nice. Later on, again from that element number 30-ish, we see that there's a stronger difference between the two. That means what you just saw, the lines start to deviate. Every time you perform the next element, it deviates a bit more and a bit more and a bit more, but distinctly from this point on. So if we plot it in the accuracy or the deviation, if you will, here's the first elements, which is very difficult to do. Other people will be talking about that today. We didn't strive for accuracy right now. We tried to find the logic first, right? Then we see all the way up to iron, zinc, gallium. There's a very nice correlation. And then it all the way suddenly starts to drop off. So the conclusions of this graph. The linear part is all the way up to iron and a little bit further even. The data sets correlate strongly. The deviation starts to come up. There are jumps in both lines, blue and red, which are unexplained, like I have to point that right there. There's a sudden jump. There's a sudden jump. There's a couple of jumps there, which are never explained by anybody, I believe. And if they do, please tell me. So, to sum it up, it seems that the elements have in actuality a more binding energy than reflected in the observed values. We calculate too much. It could be wrong, but it could also be there's another reason. That's what we're going to. So when we look at the predictive capability even from the structured atom model, splitting the atom, we have a small calculation here. And we take the differences of uranium for 235, for example, which is about 326 MeV. We plot the fission products, in this case promethium, I think, or I'm not sure, neodymium, and then you do the calculus and you end up with the 214 or so MeV, depending on what products you have. So I'm going to have to move on here. To point out another thing, here we have the depictions from Norman Cook's book, where you see the symmetry or asymmetry actually of the fission products coming off, meaning this is the 140 region, the 90 region, and they are actually completely mirrored, very, very nicely, very perfectly. We believe that is reflected in the structured atom model very nicely. And this graph too, which I cannot explain right now. A mass defect occurs in 3 instances, if you will. When you create a deuteron or a helium, you see a mass defect occurring. If you keep adding neutrons to a known element, you will also get that same effect. And as pointed out in the graph, in the heavier elements over here, you get a deviation, which is again that mass defect occurring. Supporting evidence. Supporting evidence comes from the Sapphire project. Very recently, they came out with a new video. I would like to recommend that to everybody. It's highly fascinating, well done video. It's a pleasure to watch it, and they have some very interesting results. Quickly, this is their anode, which they use in their chamber, plasma chamber, before in this case. Here it is after the experiment. And this is what they presented in that video, the elements that come off. And they were detected and validated by a US national laboratory. I do not know which one. A little bit more supporting evidence from Iwamura. We can see all these jumps here, lots of jumps. Fission, fusion, I think both are happening. And then Mizuno, already working on this for a long time. Basically, the elements are all over the periodic table, so that has to be a fission in our... thank you, I'm going to conclude. One sec. I need to do this. So we have discovered where and how much energy is hiding in which element, and that is represented by the stress energy or repelling forces between the branches of the nucleus, which is a very new concept. And the implications are that the topic of the binding energy is obscure and its relationship with mass defect is complicated, and it appears that the average dropping off of the binding energy or mass defect from iron onwards is in actuality a repelling force between the branches, which we call stress energy. You can see all the elements on our website in full 3D. Thank you so much.
Do you have a figure of merit for your mass estimations, such as the RMS deviation between the observed mass and the predicted mass?
Well, that's the whole point. What we're trying to point out here is that the mass defect, which we normally equate with the binding energy, generally speaking, it's not that simple. What I'm trying to point out is that the mass defect, we're not seeing the real binding energy. We believe that the calculation, the logic holds true, but it's diminished by this repelling force. Hence, we see a lower binding energy.
So how do you test your model against reality?
Well, I believe that, well, this is the case I'm trying to make, that we can do the calculus, at least approximately right now. This is very new. And therefore, we can see that there is this, of course, it's the mass, ESMC square works, right? But we are not seeing it because, well, we're not seeing it, so we're not aware that there is in actuality, there is more binding energy in the nucleus than we think it is. So we believe that this topic deserves a lot of attention.
But that's just an ad hoc explanation as to why your model doesn't predict reality. So how do you test your model? How do you know it's correct?
It reflects all the known attributes without a problem.
Well, let me make another comment on another slide of yours, you showed twice the fission yields for actinides when they fission. And there's a very good explanation as to why they're asymmetric, and you apply a very old established gamma theory, and that predicts, for actinides at least, a peak around the magic numbers of 50 protons, which is 10, and 82 protons, which is 82 neutrons, which will be around 10^132. So that's why the right-hand peak is almost the same for all actinides, because the gamma theory is predicting the highest energy, or higher energy, I should say, for the fission reaction. And the left-hand peak, the lighter peak, just makes up the difference.
I'm not sure. I'm not too familiar with that, so I don't think it's wise for me to comment on that right now. I would love to continue the talk for sure, the debate. Yes.
Yes, let's do that. Jacques wanted to ask a question, and we have Lutz behind. Thank you.
Okay, I come back to your table. You presented the periodic table of elements with different pictures of the nucleus. But it seems to me that you make a link between this structure of the nucleus and the chemical properties. While, for me, the chemical properties result from the behavior of the electrons at the different orbitals, which are far, far, far away from the nucleus, you know?
Very good question. The model was developed basically from the properties of the elements, i.e. the valence, oxidation states, which is a chemical domain. However, we believe very thoroughly that the properties in the chemical domain, meaning the outer electrons in this case, is dictated in first by the nucleus. So the nucleus has its organization. When it doesn't like, for example, too many neutrons, it will perform the beta minus decay and emits an electron. Therefore, the outer electron structure is dictated by the nucleus. That is the premise that we work on, if you will. Hence the connection between the physics of the nucleus and the chemistry of the outer orbitals. Needs to be developed further, admitted.
We have Lutz Joyner.
Wolfgang Pauli predicted the existence of the neutrino by observations of beta decay, beta minus decay. So there was an anomaly in the spectrum of the energies coming out of beta minus decay. And how do you explain that? If there is no weak interaction going on, if it's just an electron leaving the nucleus, how do you explain the same thing that Wolfgang Pauli could only explain by predicting a new particle?
Very good question. What we're trying to show is the structural component and the relation to all the attributes and the logic. How exactly, what happens when an electron migrates from the nucleus to the outside or reversed. That is, I believe, the domain of the electromagnetic. Meaning there are other experts here that I believe can explain or answer your question, if you will, much better. And we are trying to connect to a lot of people and to actually answer your question, I guess. It's not solved yet.
Okay.
We're going to take a last question.
Yeah, very interesting. The thing is that your calculations assume that you have only forces between nearest neighbors.
Only forces between?
Nearest neighbors of protons. I mean, maybe you should go to second neighbors, to have more precise calculation, because there are repulsive forces between protons when you have many protons. But then the calculation becomes more complicated.
It does. We're making attempts to find out exactly how that works, and there will be a few more speakers to talk about that. Okay. We believe it should be very simple. You should have a very simple algorithm, but it's not that easy, I'm afraid. And we're trying to find it out as well. This has been our first attempt to plot that stuff like binding energy, mass defect, etc., based on the logic of the structure. So it was a big tryout for us, right? If the structure was not true at all, then the data would not have made any sense. Because both data lines, the calculated we do, and the observed data, the literature value, they're not really intrinsically related. So they should not even coincide, yet they do very strongly. So we feel, therefore, it proves, if you will, the structure.
Now let's talk more at the break.